Hi everyone, so this is FALCONS, a joint work with Fidel and Lee. The goal of this paper is assessing the quality of actions in which we aim to automatically evaluate how an action was performed and what grade should be assigned to the performer. Here you can see two examples of AQA in diving and gymnastic vault. AQA can be even applicable to other fields than sports, like assessing the surgical skills of a student, but here we focus only on diving. Well, current approaches regarding automatic grading take into account either the appearance-based features or pose-based ones to regress the final score of the action. Appearance-based methods utilize C3Ds to simultaneously model spatial and temporal subspaces, but these approaches result in heavy computation costs both in training and testing phases. Besides, we also have pose-based assessors that regress the score based on the extracted pose sequence of the routine, but such methods suffer from the huge number of failures in the pose estimation of such extreme cases with unusual contortions of the body and blurriness of the image frames. And finally, most of them only use the final score to train their network, while each performance is assessed based on both the execution and the difficulty of the routine. But in our approach, inspired by what actually human judges do, we propose a virtual refereeing system that considers both pose-based and appearance-based features as the contributors to the execution score. Amount of splash can be considered as the appearance-based features, and angle of entry to the water, which should be as vertical as possible, is among the pose-based ones. Inspired by STNet, in order to capture the spatiotemporal appearance features, the 3D convolutions are decomposed to 2D spatial convolution filters followed by 1D temporal ones. The challenge of pose estimation task in such extreme cases is handled by introduction of a dataset of extreme poses. And finally, the difficulty of the action is assessed based on the joint sequences according to the official benchmark of difficulty grading. Well, this is the overall pipeline of our action quality assessor. The video is fed to a pose estimator, and the difficulty of action is assessed based on the extracted pose sequence according to FINA lookup table. On the other hand, we have a virtual referee which is responsible for awarding the execution score of the performance based on both the pose and appearance clues. Let's explain each block one by one, and first the pose estimator. Well, as I mentioned before, contortions of the body and blurriness of the images affect the performance of the pose estimator when trained on the existing datasets. And existing datasets do not cover such scenarios. So we have introduced a dataset consisting of 3,000 diving and 1,000 gymnastic wall images in extreme contortions. We have used the state-of-the-art HRNet as a pose estimator of the network. As you can see, the results of training HRNet on our dataset is convincing. Let's get back to our overall pipeline and explain the next block, which is difficulty assessor. Well, FINA, which is the official Federation of Swimming and Diving, has released a benchmark for assessing the difficulty of a routine based on the components of it. But how to get the components? We have actually proposed a simple diving classifier to do so and get the results of the rotation type, position, number of somersaults, and number of twists. In terms of the rotation type, a performance can be classified into 4 different groups: forward, reverse, backward, and inward. As you can see, given the joint's position in the takeoff and entry into the water, we would be able to determine the group of the dive. To get the position of the flight, the module looks for a specific pattern among all of the frames. In a pike position, the body is bent at the waist, but the legs should remain straight. But in a tuck position, the knees should be pulled tightly to the chest. So given the angle between the leg and hip limb, we would determine the position. For finding the number of twists, we have put a threshold on the distance between the left and right shoulder to count the switches between the side view profile and front view. Finally, we would be able to get the number of somersaults and the start stand position given the configuration of thorax and pelvis. Well, the next module is the pose-based assessor that we want to explain. So far, we have extracted the pose sequence. Here, we have used the well-known spatiotemporal graph convolutional network to regress the score based on the pose features, in which the nodes are the joints of the skeleton, the spatial edges are the limbs, and the temporal edges connect the same joint across the consecutive frames. But STGCN is not able to capture the correlation between structurally distant joints, so we have introduced virtual superjoints. Each superjoint is simply the average of its constituting joints location and may have connections with other superjoints. The first level superjoints are the hands, legs, head, and waist. The second level ones model the upper and lower part of the body. And finally, the third level ones for capturing the correlations of left and right side of the body. So 4 different STGCNs capture the correlation of the different parts of the body. The next module is the appearance-based accessor. For the initial architecture of our appearance-based accessor, we follow STNet, in which the 3D convolutions are decomposed to 2D spatial convolutions followed by 1D temporal ones. Each task is divided into T subtasks, each composed of n successive video frames. Well, the first 3 blocks apply 2D spatial convolutions to model the local spatiotemporal correlation of each subtask. After them, there are temporal convolutions upon feature maps of subtasks to capture global temporal relationship among them. Temporal dynamics between the subtasks are further encoded using TXP module. The temporal convolution is decomposed into a stack of separate channel-wise and temporal-wise 1D convolutions. Let's get back to our overall pipeline again. The last component to be explained is the bridge connections between the pose-based and appearance-based accessor. Well, why do we even need such connections? Well, some visual clues should contribute to the execution score more than the others, making the least amount of splash is more important than the other visual clues, like the smoothness of the flight. And how to do that? We should find some contribution ways to be fused with each subtask. But how to find corresponding subtasks of splash capturing frames and desired ways for diffusing? Well, the Pose Estimator provides a confidence score for estimation of each joint in all of the frames. As the performer is under the water in splash capturing frames, most of the joints are invisible and confidence scores of those frames are lower. So we would be able to distinguish those frames from others. We first take the average between the confidence scores of each subtask to form a T by J vector. The confidence scores of all joints in each subtask have been summed to form a T by 1 vector and normalized to be between 0 and 1. Finally, the output is tiled to have the same number of channels as the input of the TXP module. And the last thing to do is to update the appearance-based accessor based on these changes. Well, this one was the old appearance-based accessor. In the new one, the contribution weights are fused with the input of the TXP module. And if, for example, a subtask has a lower bridge weights, it should have higher contribution to the execution score. And we have a scale component K, which is responsible for mapping the contribution weight to be between K and 1. Finally, the weighted average of execution scores from the appearance-based accessor and pose-based accessor, including virtual pose levels, generate the execution score of the routine. Well, let's see our quantitative results and first detailed diving classification. The main task is to predict the overall score of the performers. The network is trained and tested on UNLV Dive dataset. To be consistent with existing literature, we have used the Spearman's rank correlation to evaluate the correlation between the predicted and ground truth assessment results. As you can see, our method outperforms the previous works. We also conducted an ablation study to evaluate the components of our network. We blocked the bridge connections by setting the K-scale to 1. And we removed the virtual pose levels and evaluated the performance of the network when the execution score is solely provided by appearance-based or pose-based accessor. And in the end, here are some of our qualitative results. So this was Falcons. Thank you for your attention.